Our project has 5 main objectives. First, we want to design a vertical axis wind turbine that works well in low, inconsistent, and highly turbulent wind conditions. And second, we want to compare major vertical axis wind turbine designs. And third, we're researching materials and manufacturing techniques to keep the design lightweight, inexpensive, and sustainable. Fourth, we're identifying optimal placement strategies such as rooftops, wind corridors, and building clusters. And finally, we're evaluating how these turbines could integrate with storage or the existing grid to support urban renewable energy generation. So horizontal axis wind turbines work great in open fields, but don't perform well on buildings. They need stable, high-speed winds and a yaw system to face the wind constantly to maintain efficiency. And vertical axis wind turbines are effective alternative because they accept wind from any direction, they self-start in gusty flows, and they tolerate turbulence extremely well. They also have a smaller footprint, lower noise, and are much easier to maintain on rooftops. This is why cities like Boston and London in the past have found that rooftop horizontal axis turbines failed, but vertical axis ones remain promising. We're also designing with sustainability in mind. Because the wind turbine is small, modular, and easy to produce, it can scale from a single rooftop to an array of many turbines. Using recycled materials lowers the environmental impact, and the low noise makes horizontal axis turbines suitable for community-centered deployment. To optimize lift and stability, we selected the NACA 0018 airfoil, and according to our research, this airfoil performs well at low Reynolds numbers, which matches the conditions of a small vertical axis turbine. Its thicker 18% profile increases stiffness and makes 3D printing easier and more reliable. Because it's symmetrical, it maintains a good performance across the wide range of attack angles that a vertical axis blade experiences during rotation. Our seating criteria include flat urban rooftops, areas far from tall obstructions, and locations inside natural or artificial wind corridors created by buildings. We'll also consider clustering turbines to increase overall power density while keeping them evenly spaced to avoid wake interference. This map visualizes how building heights influence wind flow. Tall buildings create large wake zones that reduce wind speeds for anything behind them. Our goal is to place turbines where rooftops rise above surrounding structures and provide clean wind exposure. And for the prototype, we're selecting lightweight composites, aluminum for the shaft, since it's a lighter metal, and primarily 3D printed components. Recycled plastics help reduce cost and carbon footprint, while 3D printing allows us to rapidly test and refine blade geometries. And in the future, when we enter mass production, 3D printing is a cheaper alternative than the traditional manufacturing methods. Okay, so flow simulations show that the NACA 0018 profile develops strong lift and has minimal flow separation at low wind speeds. And the narrow wake reduces drag and improves the overall power coefficient. These characteristics make it ideal for a vertical axis blade constantly changing direction in turbulent winds. Another profile we compared to was the thinner NACA 0012 profile. And while it has lower drag, it produces weaker lift at lower speeds and shows earlier flow separation. This makes it better for higher speed turbines, but not the small vertical axis ones we plan to deploy in the city. And this is the last profile we tested, the NACA 2412 profile. And it's cambered, so it produces strong one-directional lift, but it becomes unbalanced in reverse flow. Because a vertical axis wind turbine blade constantly reverses its relative angle of attack, this will create uneven torque and reduce efficiency. This confirmed that symmetrical airfoils are essential for urban wind turbine design. And for our CAD model, we decided to go with a rotor diameter that's roughly 50 to 60 centimeters with blade heights around 40 to 50 centimeters. We designed the blades using the NACA 0018 profile with a thickness optimized for printability. The hub fits a 12 millimeter shaft and creates uniform spacing to ensure smooth rotation and minimal vibration. So in our study, key findings are that the simulations showed that the NACA 0018 profile delivered the best mix of stability, lift, and low speed performance. Its symmetrical, thicker profile generated more consistent torque throughout rotation, and the added thickness also improves 3D printability and structural strength, making it more reliable for prototyping. The wind map analysis confirmed that the placement matters just as much as the blade design, with river corridors, coastal edges, and open rooftops providing the strongest winds. Overall, the results support a practical and scalable wind turbine design suited for real-world urban environments.